Okay, let's get started. Morning, everyone. Before we get into the main talk, I always like to start things off a little differently. I'm an Android developer, unashamedly an Android developer. It's going to be a very Android-related talk, so if there's any iOS folks in, then maybe I won't hold it against you if you want to leave now. I'm not a fanboy. I don't hate iOS. I think it's a fantastic platform. It's just Android works for me personally, so I tend to focus on Android. That said, us Android developers, for a long time, we really did have envy of iOS because, to be honest, Android was fugly. It really wasn't as anywhere near as pretty as iOS is. But there was a tipping point a couple of years ago with material design, and finally, Android looks good these days. Gone are the days of horrible orange sort of glows and things around everything, and it just looks much nicer. And it's much more enjoyable to develop on Android now, knowing you can get good-looking results. So I just want to try something with you. Just a show of hands, anyone here developed on Android before material design when it really did look ugly? So you know my pain. You know how horrible it was. So let's try something. We're going to see if we can recreate that tipping point where Android started looking nicer. And we're going to try and do it with our minds. So I hope you can see this, but I'm going to place a pen on the table. I'm going to move away. And what I'd like everyone to do is focus on the pen and imagine that we're actually pushing down on one end of the pen, pushing down really, really hard. And if we all focus and try and push down really, really hard on the pen, really have to believe we can do this. Imagine a really heavy weight on the end of the pen, pushing it down. Wow, well done, thank you. It helps if my presentation doesn't die. Let's see if we can connect up. Okay, so my name's Allison. I write this blog sort of thing that is pretty famous for having more typos than meaningful words in it. I'm not going to sort of give all the details. You can got all my contact details there. The one thing I will be doing during the presentation is I will be live tweeting. So if you follow me on Twitter, my handle is Allison. And if you follow the Twitter stream, at various points during the presentation, you'll get links to articles and further information if you want to read up on things. The one thing probably worth saying about me is my name. If you actually go into Urban Dictionary and look up Allison, you get the coolest bitch on the block, which I can live with that. I've been called much worse things, I promise you. But today, we're going to talk about vector drawables. Vector drawables were introduced as part of material, or alongside material design, and they're a key point in what builds material design, getting meaningful motion and nice graphics. So what are vector drawables? That's the big question to start with. So they're scalable graphics. So you can create a vector and you can change the size of it, and it renders well. Bitmaps, they map a single pixel, and if you try and scale them, you get blocking, you get artifacts, they look horrible, if you scale them up, that is. And they're big. Vector drawables are much smaller. They're actually based on SVG path data, which is a declarative form of graphics. You give it a series of commands, which should be familiar to most developers here. They can be animated. Now, anyone that reads my blog knows that I love making shit move around. It's great fun. It's one of my favorite things to do. Problem, they were introduced in Lollipop, so it's MinSDK 21. Until recently, earlier this year, we got vector drawable compat. There are some limitations. It doesn't do everything that vector drawable can do, and we'll cover a bit of that as we go along, but you can do some really cool stuff with vector drawable compat. And they're great fun. I really love playing with vectors. I'm never happier than when I look at my Jira list and there's something where I can animate stuff and I can use vectors here. And on the current project I'm working on, we didn't have a single vector in there before I joined it. And now we use vectors at every opportunity. The designers love it because they can just give me SVGs and then I can animate them. It's great fun. It really is. So, SVG paths. So, I've already said we're based on SVG path data. It's important to understand that SVG and vector drawable are not the same thing. Vector drawables use a subset of the SVG specification. We can only use path data. So what you may find is your designers will give you SVGs which have lots of gradients and stuff like that in it. You'll import them and you lose stuff. So it's not a one-to-one mapping between SVG and vector drawable. So you really need to understand a little bit about SVG to be able to make best use of them. So SVG paths. Here's a square. Squares are quite easy to draw. And so what we'll do is we'll use this as an example of how we can draw an SVG, a square, using SVG. So firstly, we need to understand the coordinate space. First time I did this talk, I didn't have this slide in, and it confused people because they didn't know where the point of reference was for where the origin is in our coordinate space. It's actually at the top left. So every coordinate we use is relative to that position. Initially, people thought it was bottom right or didn't know it was, and so when I was addressing those coordinates, they didn't understand why. So here is the SVG commands that draws a square. Now, initially, this looks a little scary, but it's not really, because you can break it down into component parts, and it's all really quite understandable. So the first command, M100, 100. M means move to. What that is doing is moving the current position without drawing anything. So the arrow shows where we're moving with respect to the origin. The other important thing here is the M is uppercase, and uppercase and lowercase for our commands are important. If you specify something, command using an uppercase, it's going to use absolute coordinates. Whereas if you use lowercase, it's going to be relative to the current position. So you can see here in the example, I've mixed it. So the initial move, we're doing absolute relative to the origin, but all of the other commands, because they're lowercase, we're going to move relative to the current position. So the second command is L. That is an L, not a 1 or a capital I. It's actually an L. And that means line to. So we've got move to and line to. Move to moves without drawing. Line to moves the point, but draws the line. So we've drawn the top of our square. By just the coordinates there, 100, 0, that's the x and y aspects that we're going to move. So we're drawing a horizontal line by just moving in the x direction and not in the y direction. And so the next command, another line to, we're now just moving in the Y direction, so we move 100 pixels down, drawing a line, and we've drawn a side of the square. The third command, we're using minus 100 in the X direction, so we're coming back the way we came. We've drawn the bottom of the square. The final command there, Z. Move to and line to sort of give us a hint because they sort of are the initial letter of the command they're doing. Z does something a little different. It actually means close path. Now what that does is that's going to draw a straight line from the current position back to the starting point of the current path. So in this case, it's the first line. So we do that, and it just closes the path. And it's important to use closed path because if we were to manually draw the line, we might leave a very, very small gap. And when we come to fill, all the color will leak out as well. So if you use closed path, you can be guaranteed that it's actually going to be an enclosed shape. And so if we fill it, it's just that shape that will be filled. So that's pretty simple. They're just some simple commands. Anyone that ever programmed Logo will be familiar with this. It's just telling the system where to actually draw lines. Now, there are a few more commands than this, which I'm not going to go into today, because otherwise we could just fill the whole talk with SVG path data. But you've got 3 different commands for drawing different types of curves. You've got drawing horizontal and vertical lines. I've just kept this simple, but once you begin to understand these, you can actually do some really quite interesting stuff. So how do we actually use this? So the first thing, I've broken this down into the individual commands, but when we come to use this in Android, we just put a single string in. So that's already much more difficult to read. So a top tip here is if you're trying to understand what a vector is doing, just cut and paste it out into an editor and break it down into the individual commands and understand the individual commands, and then you'll begin to get a feel for how the vector actually works. And that is important, particularly when you come to animate things. So let's start building this into a vector drawable. So anyone familiar with Android XML files will start seeing some similarities here. So we have a path data attribute, which is where we put, surprisingly, our path data. We have various other attributes that are going to control how it's rendered. So we have a stroke color, which is going to dictate the color of the outline. We have a stroke width, which is the width of that. We can put fills and all sorts of other things in there. And we've also got some other useful things called trim paths, which we'll come on to later, which can be very useful when we come to start animating things. But all of this goes into a path element. We can have multiple path elements in a single vector drawable file. So you can build up some really quite complicated graphics through a series of quite simple paths. All of this gets wrapped in a vector. So as I say, you can have multiple paths in here, and the vector really dictates the attributes of the entire image. Now, the thing that can be confusing here is we have 2 widths and 2 heights. We have a viewport width and height, and we have a width and height. Now, initially, this seems a little confusing. Why do we need 2 widths and heights? It's actually really useful. The viewport width and height define the size of the canvas we're drawing on. So with our path data, those 100s are relative to the viewport sizes. So we set up a canvas that's 300 by 300 pixels. And so by drawing inside the middle of that, from 100 to 200, we're effectively centering our square within the canvas. So that's really what's happening internally. The width and height, they're in DP. They are what's reported to the outside world about what the size of the vector drawable is. So the outside world doesn't care about our canvas size. That's just about how the renderer is going to render things. But the width and height is, if you put this into an image view and you set the image view as size wrap content, during the measurement pass, it's going to look at the drawable and say, how big are you? This is the size that it's going to report back. So when you come to measure this, that's the size it's going to be measured at. The reason this is useful is because we all know that designers can be a little fickle, and they tell us, this needs to be 48 dp, this icon. And so you do that, and they say, yeah, you know what? Be better at 36. If you had a single coordinate space here, you'd have to go in and change all your path data to draw correctly at that size. In this case, you can just change the width and height to what the designers decided upon, and the rest of it will render correctly to that new size. So having that disconnect really makes life a lot easier for us. So that's the basis of an SVG file, and you can cut and paste that into your project and drop it into an image view, and you'll get a square. It's as simple as that. But there is some other stuff we can do here. So we've got other attributes that we can use on the path. So we can specify a fill color, for example. And again, this is the point at which, if we hadn't properly closed using a closed path, we may get leakage of this fill because it's not a complete closed path. But there's various other aspects, attributes we can set here that will control how it's rendered. We can change alphas, so the transparency of objects and things like that. And all of these are just attributes. The same as we can change attributes on our layouts, we can change things in the vector drawable. So this means the actual coloring is independent of the path data itself. The path data is almost a black box at this point, but we can still change how it's going to render through changing attributes. Again, which is useful, and when we come to animate, is really useful. But other things we can do here is we can have groups. So you can define a group. A group can contain multiple path elements, and the vector drawable can contain multiple groups. Groups share an important thing with all of the other element types, including path and clip path, which we'll talk about in a second, that you can give it a name. Naming is important for two reasons. Firstly, if you name your paths and groups, it makes it easier to read them afterwards. If you come back to it in 3 months and you've forgotten what each element does, then you've got an understanding curve that you need to go through to understand your vector drawable again. If you give things a name that describes what they actually do, you're actually making it easier to understand and maintain your vectors. But they are also important for addressing individual components within the vector when we come to animate. Other things you can do at group level is you can apply things that will change the state of the canvas upon which you're drawing. So in this case, we're applying a rotation to the canvas. And by doing that, we render exactly the same path, but it's going to rotate it. There are various other things you can do. You can do translates, you can do rotations, and this will be applied to all of the child paths within that group. The final thing that we have is what's called a clip path. Now this is very, very similar to a path, only rather than drawing something itself, it actually controls about what else can be drawn on the canvas. So here, if we put a clip path in there, which represents path data that is that circle. It's not going to draw that circle. I've just put the outline there so you can see what that path data represents. What it's going to do is control which pixels can be drawn on. But it only applies to all the paths that follow it. So in this case, because the clip path is following on from the path, it has no effect. But if we swap them over, you can see that the subsequent path only paints in the area that overlaps with the clip path. So by using a clip path, you can show and hide sections of your other paths. And this, again, can be very useful for animations. And there is an example shortly that shows a clip path being used for that. So that's the basics of vector drawable. They do require some additional thought because they're a new concept. But when you break them down, they can be quite easy to understand. But I keep using the word animation. And there is another aspect to vector drawable which really excites me, and that is animated vector drawable. Yeah. So how do we go about, so we've got our square, great, boring. What can we do to it? We can animate things. How do we go about that? So we start with a vector drawable. The important thing here is we've given the path a name. Imaginatively, I've called it square. Can't think why I came up with that naming. And this is important. This is a requirement for our animation because it allows us to address an individual path element within the vector drawable. So here is our animated vector drawable. This is actually really quite simple. It's a mapping file. So at the top level, we define the drawable we're going to animate. So this is the vector drawable we looked at on the previous slide. I saved it as vector square. Again, really interesting naming. We then have a target. Now, a target is a mapping of a path element or group or clip path, a named element within our vector drawable to an animator. So the name is square. So this is the path data, which I imaginatively named square. And then we have an animator. You can also have multiple targets within a single animated vector. So you can have a lot of these mappings. So you can kick off a number of animations to run concurrently. And so what's missing now is this animator. Now it's important to note that there is, it was released quite recently, there's a new way of actually bundling these. It's called animated vector drawable bundles. And you can actually declare this stuff inline in this file, rather than have these three files, the vector, the animated vector, and the animation. And you can put them in line, and all it does is at compile time, it just splits them out again. But it can make things a bit easier to maintain because it's all contained in a single file. But here's the animator that we're using. This is a standard object animator, which has been in Android since Honeycomb. So this has been around a while, and this allows us to animate individual attributes. So you can use this on views, but you can actually also apply it to vector drawables. So all of those attributes we looked at for fill color and line color, and the translation and stuff on the groups and the clip paths, all of that can be animated. And so in this case, we specify a property name of fill alpha. So this is going to be applied to our path element, which we called square, and this is going to change the fill alpha color, the transparency. And we're going to, the value type is a float, and we're going to go from value 1 to 0, and we're going to repeat it. And so when we run that, we actually need to kick it off manually. Now this slide, I realized, is actually slightly outdated. This doesn't scale well to animate vector drawable compat. Rather than casting to animated vector drawable, it's better to cast to animatable, which is an interface that animated vector drawable implements. And that defines the start method, because this will not work with vector drawable compat because it has a different class name and stuff like this. So if you use animatable, then you can just call it interchangeably, and it doesn't matter whether you're using compat or normal or whatever. But you actually need to physically start the animation. And so if you do that, this is what you get. Okay, it's not that exciting, but it didn't actually require an awful lot of work. The object animator is doing all the hard work for us. We're not having to worry about any of the individual keyframes or doing anything like that. We just give a start value and end value and say, go and do it. And that's quite nice. Other examples we can do. So if we actually put our path inside a group, and we give it a name, square group, and we give it a pivot X and pivot Y. Now we saw an example earlier of how we could just change the rotation. So we're setting the pivot point about which we're going to rotate, but there's no rotation set in there. But when we come to our animated vector, again, we're addressing square group there, and we apply the animator. And the animator itself, the property name is rotation. This is an integer type, and we're going from a value of 0 to 360, which is the rotation in degrees. And so when we start that, with the infinite repeat and things, we can actually start rotating the square. Again, that would require a chunk of work to do manually if we were working out that rotation within code, but it's just doing stuff for us. So here's an example I really like. So here we've got a much more complex shape. This is a spiral. I've omitted the path data from here because if I put it in there, it would just fill with noise and you wouldn't understand it anyway. But these vectors are available if you want to download them and have a play, and I'll give you details about that later on. So you can grab this and you can have a look at how this spiral is constructed if you want. But one of the things I mentioned earlier was this thing called trim path. Trim path is really, really useful, particularly when we come to animate. And what trim path enables us to do is, so we've defined this path. Trim path enables us to draw just a portion of it. So you have trim path end, trim path start, and trim path mid. And they do pretty much what they say on the tin. Trim path end, which is what we're going to look at, will only draw, I can't remember which way around it is. I think it's trim path start. Trim path start will say only draw the beginning of this. And by giving it a value of between 0 and 1, we'll control how much of the path we draw. If we give it 0, it's going to draw nothing. If we give it 0.1, it's going to draw a tenth of the path. If we give it a value of 1, it's going to draw the entire path. And you can do that on the end as well. That's trim path end. And you can do it for chunks in the middle, and that's trim path mid. And you can animate this as well. So once again, we give it a name, shape. Yeah, I really didn't think that one through. We do the mapping in exactly the same way. But the object animator in this case, you can see we're doing trim path end. It's a float type, and we're going from 0 to 1. And so by doing this animation, it's as though the path is being drawn in real time. And if you've got some shapes and you want to display them, I believe it was Romain Guy did a really nice demo where he had outlines of US states, and as they displayed, the outline was drawn. And he did that before the days of vector drawables, and he did this whole algorithm to effectively do a trim path. But now we get it for free, so you can define quite a complex path. But just by applying a simple animation like this, you can do some really quite nice effects. And the real power, when you really get into the bones of this stuff, is when we actually start animating path data itself. Now, at this point, it is worth pointing out that everything we've covered up to now is supported by both vector drawable and vector drawable compat. So all of the examples up to this point will work across the board. This is where we have a limitation with vector drawable compat. It doesn't support path data animations. That's the only big limitation. Now this looks quite scary. We've got these two paths here. And it's not immediately obvious what this is going to do. But the important things are the property name is path data. So this is the path data element attribute within our path. We're going to change this over time with an animator. The value type is path type. So where we had int and float values before, we're telling it this is path data. And finally, we have the value from and to are two lots of path data. They're two paths. So let's break these down. They're actually a square and a triangle. What is important is you need to match the number and types of command. Now, when we drew the square, it took 5 commands to do that. The initial move to set the position, and then the 4 sides. Now, some of you are probably ahead of me and thinking, Mark, do you think we're stupid or something? Everyone knows you don't need 5 commands to draw a triangle. A triangle has 3 sides, a square has 4 sides. Therefore, you should be able to draw a triangle with 4 commands, a move and then 3 sides. And you'd be absolutely correct. But if we want to animate between those 2 shapes, we need to think a little creatively. So let's look at how we're actually drawing these 2 shapes. So we start with the move to. It's the same for both. We're moving to the same start point. And the first line that we draw, again, there's no change there. Where we start to change is when we draw the third line, the second line. For the square, we're drawing the right-hand edge. But with the triangle, we're drawing down to the bottom point. Now, this is where it becomes a little weird. The third side we draw is a pretend side on the triangle. We actually do nothing. We just stay put. This corresponds to the bottom edge of the square. And then when we do the closed path, you can see, again, the value of closed path. It automatically draws that final side for us on the triangle without us having to work out the maths of what we've got to do there. But the important thing is that pretend side on the triangle. It doesn't really exist. But that is key to how this animation is going to work. Because then if we animate between those 2 path states, we can actually see that we are morphing a square into a triangle. And it's that pretend side that's actually collapsing in. And so by understanding where we're putting in these fake elements, that helps us to control, okay, we want this to collapse in this particular way. But it is important, if you do not match the exact number and types of these commands in your path data, it will just fail. It will just be unable to create the animation, and nothing will happen. You'll probably get an error. But you have to match the types and number of commands, otherwise it will fail on you. So sometimes you might need to make your shapes a little more complex in order to animate them into something else, in order to morph them into something else. So again, a simple example here, but that's why you need to draw a triangle with 4 lines rather than 3. But this is another example of a morph that I did. This is a bit more complex. This actually required drawing a square with curves because the circle has curves, and so you have to match the curves together. And again, I'll give you details of how you can get this if you want to have a look at it, play with it, pick it apart, and do your own stuff with it. It took a bit of work to get it right, but it's quite a nice little morph. But then you can combine all of these techniques. So I said earlier that you can put a number of targets inside a single animated vector file. And by doing that and applying different animations, here we've got a number of things going on. We're actually drawing 2 paths. One represents the outline, and one represents the fill. The outline is at the top, the fill is lower down, and between the two we actually have a clip path that we're animating, and that's what causes the fill and empty of the shape. We're also animating the outline, just like the last one we saw, morphing the square into the circle. And then we've got a rotation going on. So the individual components are much simpler, but you can actually get quite a complex animation just by layering up these different animations and techniques. And so here's some other examples. This was something I did for a floating action button. What I wanted to do was when you click the button, it actually opened a submenu, and you had a sort of an expand and collapse. And again, I used the concept of having a 0 line, a pretend line, as one of the states, and then by animating between the two and putting a little rotation on, you can actually animate between a plus and a minus. And so when this was triggered by a touch on the fab as it expanded out, and tying that in with the duration that the expand was happening, it creates a nice flowed effect, very material, material motion, that kind of stuff. Another example, hopefully we're all familiar with this guy. This is imported as an SVG. I grouped the arms and the head together, and by applying a simple translate, you can just make him chuckle. And a final example, this is one I actually blogged about quite recently. This is, you can do some really useful effects. Hopefully those that are following the Twitter stream will have a link to this, the blog post, which it ran into a few articles, mainly explaining some of the underlying principles that I've done. But this is just a series of paths. Just like everything else, it's a series of paths. We're drawing a number of distinct shapes, and then by applying animations to those and changing the color as we go, we can actually create quite a believable sort of terraforming sort of animation that you might see in Minecraft or something along those lines. And that's pretty much it. There's loads of stuff out there. I've written quite a few blog posts on this stuff over the years of different techniques. If you haven't played with these things, I urge you to. They're great fun. You can really have enormous fun. And there's nothing better than when you go back to your designer and say, oh, I managed to do this, and see their face, see their reaction. Sometimes it's a bit negative because they think, well, we're supposed to do the animations. It's not supposed to be the developers that do that. But you generally get a really positive reaction from designers. They like to see these kinds of details in there. And once they start knowing you can do it, they'll ask you to do them. And you get to do them more often. And as I say, I make no secret of the fact that I love doing this stuff. So that's about it from me. I hope you go away, play with these, learn them, get familiar with them, enjoy them. Thanks very much. Now, just before we open up for questions, I should mention one thing. A common question that gets asked is, are you going to release the slides? The answer is no, I'm not. Now, I know what you're thinking. Mark, you bastard. Why aren't you going to give us the slides? The reason I'm not going to give you the slides is because there aren't any. This is an Android app. This is running on a Nexus player. I have it linked to a Pixel C, where I have my speaker notes that I completely ignored. My clicker is actually the remote control for the Nexus player. It's an Android app. There are no slides, because every slide that you've seen is actually an Android layout. The animations are all Android animations. All the page transitions are using the transitions library. And it uses vector drawables. So every time you've seen an example of a vector drawable on the screen, it's not been me capturing a GIF and putting it in a slide. You're seeing that rendering real time. So they are real vector drawables that have been displayed on the screen as we go. I wrote a blog series. I first started using the app a few years ago, and I wrote a series explaining some of the concepts about how it worked. And it's open source. There's a Bitbucket repo. Those following the Twitter stream should get a link to both the blog series and the Bitbucket repo. All of the vectors that you've seen on the screen are in the repo. So you can grab them, you can play with them. So yeah, I apologize that there's no slides, but grab the code, look at the code, understand the code. Surely that's better than slides for developers. So that really is it from me. So we'll open up for questions, but I always like to ask one question before we do that. Did the Twitter stream work?
Yes.
Excellent. I love it when a plan comes together. So yeah, thank you very much. So any questions? I think there's a mic coming. Okay, for anyone that didn't hear, the question was, what would you recommend if you want to create that path data on... there are a number of tools out there. The one that most of the designers will be using is an application called Sketch, which is a graphic design drawing utility. You've got Adobe Illustrator. Doing the path data animations pre-Lollipop, you're going to struggle. It really doesn't work on the Compact library because the APIs to do it just didn't exist pre-Lollipop. Even if you tried doing your own by directly drawing to canvas, you're going to struggle because some of the underlying APIs aren't there. So you really do need to consider what you can and can't do pre-Lollipop. Having said that, using all of the other techniques, apart from path data, you can really do some quite incredible stuff by bringing them all together. So the example I gave of the spinning, morphing square, which was filling and unfilling, that would all work pre-Lollipop because we weren't, sorry, no, it won't because the morph was path data. So no, forget I said that. But you can still, on my current project, I was tasked with doing an onboarding animation. So I got an SVG from one of the designers, and I broke it down into groups. And just using those tools, I was able to put together a really quite smooth and intricate animation without having to touch the path data. So by using alphas and translates and rotates and all of that kind of stuff, and clip paths, animating clip paths is really powerful. By using those techniques together, you can still do some pretty amazing stuff.
Hi, Mark. Great talk, by the way. So I have a question. So there are a lot of elements in SVG that aren't supported yet in the vector animation. So what are some elements you would like to see in the near future?
That's a tricky one because one thing that designers will always want is gradients, because designers quite like gradients, even though they're a little passé in material terms, which is much more about flat colors. But gradients are expensive to render, and I think it's quite a conscious decision to leave those out, because they wanted, the designers behind the Android framework wanted to keep this stuff performant, memory efficient. And that's certainly something that you might see if you're using vector drawable compat. Sometimes you can get things that will render nicely without it, that don't render quite as well with it in terms of animation, because it runs out of memory to load up all these animators, particularly on older devices with smaller memory. If they started putting things in like gradients, then it's going to make that problem worse. So I actually think that they've just reached a point, a cutoff point of a clean subset of the commands. I think what I would like to see is further improvements on the vectorable asset import, which is, it's improved an awful lot since it was first released, but the tooling around being able to import this stuff is the important stuff. Quite often you'll find if you import a file that a designer gave you, it will lose all the color information and you have to go in and put it in manually, which is good if you need to understand how the graphic works in order to animate it. But really, that's really the main area of improvement I'd like to see.
Okay, thank you.
So any more? Have we got time for any more, or is that it? No, I think that's it.
I've got one more question over here. You've said about limitations. I've got a question about animated vector drawables. Mm-hmm. Is there any limitation of size in density pixels of the image that we want to animate? Because I know we need to calculate animation and render the bitmaps under the hood.
That's a difficult question to give a straight answer to, because no two vectors are going to be created equally. The number of paths, the complexity of the paths will have a bearing on that. The number of individual animators is going to have a bearing. So there's no real hard and fast rules. Sometimes what you may need to do is just find out what works and then try and simplify if you're finding things that aren't. So as an example, this onboarding animation that I had, it's got about 12 different animators that run. And what I was finding was it was stopping halfway because it was running out of memory to load all of these animators. And what I had to do is strip out some of the animators. And what some of them were doing were just setting the initial state. So it was an animation that was running instantly and just setting a state value. And by taking those out and setting default values instead, it reduced the number of animators, and so the whole thing then worked again. But as I say, there's no hard and fast rules. It's really going to vary very much dependent on each vector drawable and the number of animators in question.
And devices.
Devices, of course. Amount of memory. As I already said about vector drawable compat, can be a bit less memory efficient, and so on and so forth.
Okay, thank you very much.
Okay, and if that's it, thank you very much.
Time for last question, maybe.
Oh, is there time for one more? Is there one more? No, don't think so. So, thank you very much. Enjoy the rest of the conference.